let's talk about arteries and veins. So the driving force for the blood flow is pressure difference. So we already learned that in the respiratory system of our breathing, also there's a pressure difference from the atmosphere to our inside lung alveolar pressure drop. That makes this respiratory ventilation. So P pressure in alveoli minus pressure of this atmospheric makes us to breathe, that pressure difference. In comparison, in cardiovascular system, we can consider two kinds of pressure difference. One is along the vessel, which is axial pressure drop, is driving force for our blood movement along this flow. And another aspect we have to see is look at this blood vessel inside of the vessel pressure and outside interstitial fluid outside. So this pressure difference is important. This inside pressure should be higher than outside to have the vessel inflated, okay? And also, especially in the capillary, where the exchange happens. And this pressure difference determines the rate of water movement out of vessel into the adjacent tissue. So that pressure difference we call the word is in English called a mural. So transmural pressure difference, which is defined in this way. And also cyclic variations in pressure, and especially in heart and arterial side, which is very elastic, which sends this pulsatile flow. So cyclic variation in pressure changes leading pulsatile flow, we can even feel and understand. And that's due to their smooth muscle layers in vessels, which can contract and dilate in response to our physiological needs. So let's consider the distribution of pressure within our vascular system. This distribution, by the way, can change upon the physiological need. So for example, when you lie down and suddenly stand up, actually the need for the pressure in physically is different. But our heart and our system will respond to that. So for example, from basic physics, you see there's a water pipe, and there's atmospheric pressure. Near here, there's a pressure P1, and there's a water or blood. Then out of this distance H, the pressure at this P2 will be higher than P1 by the amount of the gravitational force. So the P2 is P1 plus density times gravitational constant G times the distance. So we can have a fun test finding out our radial artery. Radial artery is here. So thumb, so that part, you can, near the thumb part, you can feel the pulse. Can you try it? You can feel the pulse. So feel this pulse, and then try to raise up very high, like a meter high, and then feel the pulse, and then come back, come down. And if you're sensitive enough, you may feel that pulse is different. And when you raise, it's lessened. You can calculate it. Try to calculate, because you remember the previous radial artery is about pressure of 100 millimilli Hg. And let's say the displacement from here to here is up to 1 meter, then what will be the pressure difference, which is density for water is about 1,000 kilogram per cubic meter times G gravitational constant 9.8 meter per square seconds, and H, the distance is about 1 meter, which turn out to be about like 70 millimilli Hg. So it can have a big change, and you may feel through this self-test. So this is your radial artery. So let's come back to review our actual pressure drop in our circulatory system. So look at our heart. Let's start with the right atrium. So this right atrium collects the deoxygenated blood into right ventricle, and that pushes this blood to the lung through these two lungs as a pulmonary artery, and then it oxygenates and comes back via pulmonary vein to the left atrium. And that left atrium passes the blood into the oxygenated blood into the left ventricle, and that left ventricle is the heart, the biggest pump in our body, because it pushes this oxygenated blood through the aorta throughout upper and lower body. So upper and lower through capillaries of head and forelimbs, and lower body, abdomen, and hind limbs. And that eventually, after the oxygenate and exchanging gas, it will come back. So what about the pressure distribution? So left ventricle, left ventricle contract and expand, contract and expand. And because of that, the pressure is really go up and down, but the average about, normal pressure is 80 to 120, and it goes down. And when it's high is when the heart is compressing. So this part is called systole. And when it's expanding, then pressure goes down, and that in that case we call diastole. So systole and diastole. While when we go to aorta arteries, it goes down. Arterioles, it drops dramatically because the radius going down and through the capillary as well. And venular vein, vena cava, it keeps going down, very low pressure. So with that, we'll stop it here. Next time, we will get into anatomy of the heart and the electrical system that coordinate the heart contraction and the cardiac cycle. Thank you very much for your attention.